we have Andre Miner, who's a lecturer at Sonoma State, give a talk. Andre got his bachelor's degree in pure mathematics at UC Berkeley, and his PhD was in several complex variables at UC San Diego. He's been at Sonoma State for a couple of years now, and he's teaching a variety of classes of the calculus. And today, he is going to tell you about motivational forces, an introduction to mathematical physics. So please help me welcome Andre.
Hi. Yes, thank you for inviting me to talk today. So like Brigitte said, when I was in grad school, I studied several complex variables, which means I did analysis of manifolds or calculus on manifolds over the complex field. So when I was studying this stuff, I had to learn about differential geometry, algebraic geometry, real analysis, complex analysis, partial differential equations, among other things. And so these are all different fields in math. And so when I was learning these subjects, I figured everything's pure math. There's no reason for these to exist other than that they're fun and people like me enjoy doing them. And at some point along the way, I started realizing that these things existed for some reason. Okay, these lights are not working. My first hint was that I was taking real analysis, and there was a group of maybe 4 or 5 econ grad students taking graduate level real analysis. So if you take real analysis, it seems very abstract. It doesn't seem like it's useful for anything. But somehow these people were being forced to take this class because they needed it for economics. And so I still don't know exactly what they were using it for. But nonetheless, that was a hint. Okay, so somehow some of these abstract mathematics, they're useful for something. And so there's other examples. But then eventually, I started getting more into my thesis, and this equation keeps appearing. It's called Einstein's equation. And now, okay, Einstein was a physicist. He worked on relativity. And now here in my math, which seems completely useless to everything, here's this Einstein's equation. It had to do with curvature operators on manifolds in higher dimensions. Okay, well, Einstein was doing, all I know about is, okay, curvature of space-time and gravity warp space and things like that. Okay, so the curvature of space-time must have something to do with this stuff I'm studying, this calculus on manifolds. And sure enough, so I started looking into it, and all these subjects in math that we're taking, their roots, at least, their beginnings started in the physical sciences, primarily physics. And so then I got really interested in that. And so a hobby of mine since then has been trying to figure out why I studied all this stuff I did in grad school. So this is a phenomenon that I think really is why math exists today. So someone solves a good problem in real life, whether it's a farming problem or engineering or something, and then maybe that same person or maybe someone else, they take their solution to this problem and they write it down. And in the process of writing down solutions to problems, usually you are formalizing this idea into mathematics. So this process keeps happening where people solve ideas and then they write them down, and then they take this idea and maybe they generalize it and they get a new idea, and this process continues, and eventually people start liking this mathematics without really thinking about where it came from anymore. And so there wasn't ever pure mathematicians before. At one point there was, and what happened was that people started just studying this mathematical ideas just for the fun of it, without really caring about their physics or their chemistry or their engineering that they were working on. And so people came up with mathematical results purely. And I think that most people, at least most mathematicians, hope at least that their results they'll have some use to someone somewhere, but they don't really care. They just like to do the math. So as this process continues, what you end up with is this web of mathematical ideas. And these days, this web of math has gotten so big that no one person is even close to being capable of understanding everything. And it's really complicated. And so there's a whole community of mathematicians who do just pure math. And then every once in a while, someone who's kind of a mix, maybe they like math but they do other things, and they figure out that, oh, this math result here that someone came up with 50 years ago turns out I can use that result to solve this problem in physics or in economics or in engineering. And so that's always the big deal, is when someone takes, it's a big deal to solve pure math problems, no doubt. But it's even a bigger deal when you take a pure math result and you solve a real world problem with it. So part of the problem with this web of math that's been created is that the more complicated the math gets, the more difficult it is to connect the math to the real world and other problems. And even in math itself, there's so many different fields in math now that we have algebraists and we have topologists and we have analysts, and you can be in one field of math and have pretty much no idea what someone else is doing in another field of math. So now compare that to real world problems in all of math. It's really hard to solve these problems that exist in the real world using math that exists, because it takes many connections of people. Well, okay, this guy knows about this math, and this guy knows about that math, and he knows about this, and this guy knows about that guy, and this guy, and that guy has this problem. And how do you solve that problem and connect it to the math that will solve it? So that's its own problem. And I think technology is going to be the solution. The more complicated the math and the science get, the more we're going to need to rely on a solution to make the connections for us. Okay, so I want to talk a little bit about how math has evolved, right? So the idea is that math is invented, and then someone realizes that it can be used to solve an external problem, and that gives that subject at least momentum. And so then maybe this subject solved this problem, so then this institution gives more money into people who want to study that subject, and then they get more students, and more people study that subject. And the next thing you know, you've taken this concept and you've expanded it into this generalized, abstractified nightmare of mathematics that it can be really difficult to study, and it's really fun for the people who are studying it, but everyone else is totally lost. But then what happens is, if a subject is really important, then people try to simplify it, and they make a really concrete curriculum for studying it, and eventually there's a book written about it. And then maybe if it's really important, people keep studying it, and maybe they'll finally teach a class on it. And that's how, for example, calculus became what it is today. So people realized that calculus was important, and it took a long time to formalize it. And nowadays, what we have is this really step-by-step procedure for understanding the concepts of calculus. And that's what I think most people in this room have probably taken at least Calc 1. Okay, so in the last 100 years or so, this process of this evolution of math and science has really taken off, as we all know. And things have gotten much more complicated. So even to talk about these concepts from 100 years ago, like relativity, the math you need for that is pretty complicated. It's beyond a high school level education. And I hope at least that one day maybe that'll change. Maybe we'll change the way we teach math in such a way that kids in 100 years out of high school will be able to understand the concepts of say, general relativity and quantum mechanics and things like that. But for the time being, most of us do not have the mathematical background to study these advanced physical subjects. So for today, what I want to do is I want to show us how the math we learned in high school and what calculus we've taken can be used to answer or to analyze problems in classical mechanics. And so here I have a ramp for us. And what I want to do is I want to collect some data with my ramp here, and I'll write it down, and that'll be our experimental data. And then I want to write down some formulas that hopefully look familiar from our calculus classes, and I want to show that all this jargon that we learn in calculus, it's there for a reason. It's there because it's consistent with physical results, with tangible things you can see. Okay, so I have 1.5 experiments here. My first experiment is take a board. You can do this at home. Anyone can do this. And sand it off if you can. Make it nice and smooth. And you can use rubber bands, or I use tape here. You can use anything so that when you roll a marble on it, you're going to hear it when it rolls across. Okay, so I'm going to do it once, and my marble might go flying. So let's see what happens here. Hold on. Try again. That's okay. Okay, hold on. One more time. Hold on. Okay, that's pretty close. Hold on, one more time. I've done this like well over 1,000 times. Okay, so eventually I'm going to get this right. Okay, so you should hear something when I do this. No, that's not good. Don't worry, it's okay. No, that's not good. Oh my God, this is the worst I've ever done it. Okay, that was a good one. So what you hear is you're hearing. Thank you, Sam. Thank you. What you're hearing is the marble falling off the tape each time. And so here's the experiment: is put your first piece of tape or your first rubber band right or somewhere, anywhere you want, and then the goal is to place the next tape or rubber bands so that the time interval between each tape is equal. So right, the distance is obviously not equal, but the time taken to travel across each interval is equal. And you can hear that. That's why I like this experiment. You can just hear it. You have a sense of rhythm. We all have an internal sense of rhythm, some better than others, me not so good. Nonetheless, I can hear that the rhythm as it rolls across is pretty much even. Let's see here. 5, 6. Right. 1, 2, 3, 4, 5, 6. Right. It's even. All right. Now you can. Hold on a second. Oh, this is going to make things even worse. You can change the slope. Oops, I'm hitting those things. You can change the slope of the board, and now the time taken will be longer, but it should still be even. I hope this works. Here we go. Nope, not even close. Hold on. Give me a second. 2. Oh, no. Okay. 1, 2, 3. Ah! Hold on. No. 2, 3, 4, 5, 6. Okay, well, kind of screwed up at the end. But yeah, so see, the intervals are still even though it's at a different slope. So somehow this configuration of my tape here is independent of the slope. So to get even time intervals, there's something special about this. And so I don't know if you can see it, but if you look, so this first interval. Okay, so and now this is some distance, right? And I don't want it inches, I don't want meters, I just want a unit of space. So, what's your name? Yeah.
Oh, Eric.
You're Eric. Okay, so this is an Eric now. For the next hour, an Eric is this space distance, okay? So we have new units. Now what about, now I need a time unit too. So the time it takes to go from here is equal to the time it takes to go from here to here. Young lady right there, what's your name?
Alex.
That's an Alex. Okay, so an Eric is now a space unit. Here we go. Okay, so it's about that long. That's an Eric. I happen to know it spells with an H. He's my student. and the time is an Alex. Okay. Alex. Okay. So what I want to do is I want to count how many Erics it takes per each interval. And luckily I've marked them here for us. I don't know if you can see them. So that's one Eric. And actually, so let me do this. So this is let's make a table. Here's the interval. And here's the number of Erics. Okay, so we have 6 intervals. 1, 2, 3, 4, 5, 6. Okay, so the first interval is 1 Eric by definition. The second interval, if you count, it's 1, 2, 3 Erics. The third interval, if you count, it's 1, 2, 3, 4. It's 5 Erics. The next one is going to be 7 Erics. The next one, if you count, it will be 9 Erics. And what do you think the next one will be? 11. Okay. Right. So there's a pattern, right? So already, what we see here, and of course, if I had an infinite plane, right, I could do this forever. And the pattern would be that we get this sequence. A sequence is a mathematical concept, and it's a ordered collection of numbers, which in this case are going to be all odd numbers. Okay, so this is some experimental data. Now, I want another piece of information I want is going to be the total Erics traveled. Okay, so this is easy. You just, instead of counting each interval, you count from the beginning. Right, the first one you've traveled 1 Eric. But at the end of the second interval, you've traveled 1, 2, 3, 4 ergs. Right, that's 3 plus 1. After the end of the next interval, you've traveled 5 plus 4, that's 9 ergs. At the end of the next interval, you traveled 7 plus 9, that's 16. 16 plus 9 is 25. 25 plus 11 is 36. See another pattern. What's the pattern? Perfect squares, correct. All right, okay, so now, this is where it's easy to get distracted as a mathematician. So I have all this great physics I'm doing here. Forget all of that. The sum of the first consecutive odd numbers is a perfect square. Is that true? Yeah? Was that a question? Or a statement? Yeah? Yeah.
Not just a perfect square, but a perfect square of the interval number.
Oh, great. Right. Okay, so okay, I don't want to get too distracted here, but I got to say something about this. So I'm going to use a little summation notation. I hope you're okay with it. The sum of the first 3 odd numbers is 3 squared. The sum of the first 4 odd numbers is 4 squared, and so on. The sum, I'll write it in words first. The sum of the first n odd natural numbers is n squared. Okay. Now I'm going to write that in mathy land. Here we go. The sum from n equals 1 to infinity. Oh, no, infinity, excuse me. I've been doing series in class. I've got to stop doing that. So sorry, I should do sum j equals 1 to n. There we go. The first, what does an odd number look like?
2n plus 1.
Yeah, so in this case, that's right. In this case, I'm going to do 2j minus 1. The reason being that when j equals 1, I have 2 minus 1 is 1. When j equals 2, I have 4 minus 1 is 3, and so on. All the way up to the nth one. And that's because supposedly that's equal to n squared. Okay, so now if you were an experimental physicist and you saw this table, you'd go, oh, okay, it's proved. Right? And this is actually true in general in the physics community. Physicists tend to accept proofs that mathematicians find jocular. Right? So, and this is true actually. So in physics, there are results that are considered true that mathematical physics have not yet proven, and these are kind of few and far between, and they're sort of abstract. But nonetheless, physicists tend to accept proofs like this. But as a mathematician, we want to really understand why this is true. Okay, so I'm afraid I'm going to run out of time. I can think of 2 ways to prove this off the top of my head. You could do a proof by induction, if you know what that means. And those are real fun. I think you could do that. And there's also a nice formula that you can prove this really easily if you believe this. And, I forget the guy's name who's given credit, but the sum of the first n integers, not odd integers, but just the first n integers, does anyone know what that is? Right, yeah. So I ended up using this formula an awful lot in my thesis, so that's engraved in my bones. So using this formula, I can prove that pretty easily too. So give it a try. This is an exercise. Okay, give that a try if you want. Come talk to me later and we'll prove it together. All right, that was fun. Back on track. I want to do one more experiment here. And so this is an experiment I've already done. It took me a long time to get any kind of an accurate reading. But I want to measure in true seconds, not in Alex's, but in seconds, how long it takes to get from here down to there. And I'm not going to risk rolling the ball anymore. It's just going to make a mess. So for one thing, I did it on the other side of the board where there's no tape. And I sanded my board as best I could to prevent friction with the board. And I did it just more than 100 times. I was using my smartphone, and I just kept timing it. How long does it take for the ball to roll down to the bottom? And so this is what's called this experiment 1. So experiment 2 was just to time taken to reach the bottom. And I want to point something out here. So I was much more precise with this experiment. I had it, maybe not quite like this, but I had it so that this was 10 inches up off the ground. And I measured my board, and the length of my board is 72 inches, which is 6 feet. And the time taken was about, and it was very difficult for me to get a very accurate reading. I needed to be accurate up to at least 1/100th of a second, and it was about 1.66 seconds. Okay. All right. So this is our experimental data. This was not achieved by any math by any means. It was just observed. So what I'd like to do now is use the math that we all know to analyze this and come up with some theory. We're going to model this system, and we're going to see if the math that we know predicts the results that we got experimentally. And of course, this is how physics works. This is how science works. It's this marriage between coming up with a theory and a model, and then seeing if that works in the real world. Okay. All right. So the first thing I want to do is I want to try to model what's going on here. And as usual with most things that involve change, we need a function. And in this case, so here's the theory. Well, what we have is we have a ramp, and we have this marble that's starting at the top of it and rolling down. And I'm going to let my function, I'm going to call it s of t. And I'm going to let it be the distance from the starting points after t seconds. Okay, so s of t is a distance quantity, and I'm either going to use inches or feet. Probably feet. Okay, and now it's possible that we could analyze s of t without calculus, but the whole point is that calculus makes life so much easier. And actually, so I've been talking to my students, my calculus students lately, and they're saying, not so much of a complaint, but more of an observation, that when in their physics classes, they're given these formulas and they don't know where they come from. And in their math classes, they do all this math, but they don't understand why it exists. So there's this gap between math classes and physics classes where you don't understand why they're related to each other. And my goal here is I want to make it clear that calculus exists for a good reason. Okay. All right. So I want to briefly discuss what derivatives are, and I decided, has anyone here not taken Calc 1? Okay. So some of you haven't. Okay. So you got to just bear with me here. Okay. So I'm going to define some things intuitively, and I'm going to write down some formulas that you won't understand, but then take calculus and you will. Okay. All right. So the derivative of a function is its rate of change. And the study of rates of change is infinitely interesting and complicated. But so here's a definition. S prime of t equals the instantaneous, I'm going to explain this in a second, instantaneous rate of change of S of t at time t. Okay, so the concept of instantaneous rate of change is fairly intuitive to most of us because most of us drive cars. Okay, so if you're driving your car and you're going 20 miles an hour and then you put your foot on the gas and you speed up to 40 miles an hour, well, for example, there's going to be a unique time, one moment in time in the middle there somewhere where your speed is 30. So there's one point in time and only one point of time where your velocity, your speed, is 30 miles per hour. So the instantaneous rate of time, it's a quantity that's measured at just a single time. And so intuitively that makes sense, that if you're going from 20 to 40, then there's this one unique time where you're going 30. But mathematically, it turns out it's a bit more complicated to get your hands on this idea of instantaneous rates of change. And indeed, it took hundreds of years to develop what we now call calculus. And calculus gave us this great mathematical framework where we could really get our hands on what instantaneous rates of change were. And in terms of physics words, if your function, in this case s of t, is representing position, the derivative of your function is going to represent the rate of change of your position And that's, by definition, velocity. Okay. Let's board through. Okay. And now, what are the units of our rates of change? So let's say S of t is measured in feet. Let's stick with feet. And if time is measured in seconds, like I did here, the rate of change of our position is, the units are going to be, what do you think? Feet per second. So this is a unit of a rate of change. It's how many feet you're going for how many seconds have passed. Okay, and now the other concept that we're going to need is the concept of acceleration. And acceleration is, by definition, the rate of change of your velocity. But like I said, derivatives are rates of change. So if acceleration is the rate of change of velocity, then acceleration is going to be the derivative of velocities. Oh, I didn't. So let's call this. So it's going to be the derivative of velocity, which is the second derivative of our position. The first derivative of velocity is the second derivative of position. And the units of this are going to be, well, rates of change of rates of change. So it's going to be feet per second per second. It's how quickly your feet per seconds are changing per second. And we abbreviate this as feet per second squared. Okay, so there's this relationship between these physical concepts of acceleration and velocity and these mathematical concepts of derivatives. And what I want to do is I want to do some calculus to study what's going on with this marble. Okay, so there's a classical experiment. I was thinking about doing it here, but I didn't want to break the floor. Because if you take, let's say, a bowling ball and a tennis ball, right? They're going to have different mass. But if you drop them, and you ignore wind resistance, they're going to hit the ground at the same time. So what that tells us here is that acceleration due to gravity is independent of the mass of an object. And let's say you have a feather in a bowling ball. Well, the feather is going to hit the ground at a different time, but that's because of wind resistance. Sure enough, if you make a vacuum and you drop a feather in a bowling ball, then they're going to hit the ground at the same time. So if you ignore wind resistance and other factors, the acceleration acted on a ball by gravity is independent of its mass. And so that means that acceleration due to gravity is going to be some constant. And now here I'm on my ramp. Okay, let's ignore friction. It's nice and smooth. Okay, and now the acceleration of the ball going down the ramp is still going to be constant because gravity is the only thing acting on it. But some of that acceleration is essentially being absorbed into the board. So the acceleration of the marble going down the ramp is still constant, but slower. So I want to call that something. So let's say that the acceleration down the ramp is some constant. Let's call it A. And it's going to be measured in feet per second squared. Actually, well, it's either going to be measured in feet per second squared, or it would be. We could also measure it in Eric's per Alex's squared, and I'll talk a little bit about that in a second. Let's see. And so, if our acceleration is this constant, then that means, and s double prime is our acceleration. Okay, that means that s double prime of t is this constant A. Okay. So now, this is the part. If you're taking calculus, you just got to take my word for it. What I want to do is I want to find s, and this by the way is called a differential equation. And it's at the heart of why calculus is important. We need to in order to find s, I'm going to anti-differentiate this twice. In other words, if I know what s double prime is, well, s prime is going to be a function whose derivative is the constant a. Okay, well now we got to channel our inner calculus 1 here. I'm thinking of the power rule. I remember that the derivative of something is constant. If I have a function of t, the derivative of it is constant. Well, that's going to be the next one. You're thinking ahead. At, there we go. So right, at, the derivative of at is a. Now, again, if you haven't taken calculus, take calculus. But there's a catch. Plus c, right. any function of this form has derivative a, and any function whose derivative is a is of this form. So there's a whole continuum of such functions, as c varies over all real numbers, and this marble has a unique value of c. So now I want to think about that. Okay, it's okay. So let's see here. So this is another exercise in instantaneous velocity. When I first let the marble go, that moment of time, the exact moment I let it go, what's the velocity? 0, right. And immediately after, any small fraction of a second later, it's moving, its velocity is positive. But for that moment, its instantaneous velocity is 0. So that means that the initial velocity of our function, the initial velocity is 0. That's what that means. The initial velocity is 0. But we know that s prime of t is of this form. So that means that it's equal to, when I plug t equals 0, I get a times 0 plus c. Well, it doesn't matter what a is. A times 0 is 0. So this is just equal to c. Therefore, I'm going to move this up so we can all see it. Therefore, c is equal to 0, which means that our velocity function is just a times t. So that's our velocity, a times t. Now I want to do it again. I want to find s. All right, well, if s prime is equal to a times t, I want to find s. Well, again, I need to anti-differentiate. Channel our inner calculus, think of the power rule, find a function whose derivative is a times t, and I heard it before. 1/2 a t squared, right? Yes. So what we conclude then is that our s of t must be of the form a over 2 t squared plus a constant, potentially. I'm going to use d. Right? So once again, any function of this form has derivative at plus c, or at, excuse me. And any function whose derivative is at must be of this form. And once again, we can solve for that constant t. Right? S of t, let's remember what S of t was. It's right here. S of t is the distance from the starting point after t seconds. After 0 seconds, what's my distance? 0. So that means that S of 0, over here, I know that 0 equals S of 0. Well, again, S is of this form, so that's a over 2 times 0 squared plus d. Well, again, it doesn't matter what a is, that's 0, so this is d. Therefore, d equals 0. Therefore, the function, the unique function that represents the motion of our object is the function s of t equals a over 2 t squared. Okay. All right. So that's. I want to compare something. This right here. This is all experimental data. This, and this. Everything since then. This has all been purely thought, theory. Now, what I want to do is I claim that our experimental result about finding the position function of our marble is consistent with our experimental result. Okay, so let's make a table. I'll do it over here. Okay, so here's t. Here's s of t. I'm going to let t equal 1, 2, 3, 4, 5, 6. Let's make a table. S of 1, if I plug in t equals 1 right here, well, I get a over 2 times 1 squared. If I plug in t equals 2, I get a over 2 times, well, 1 squared is 1, but what's 2 squared? 2 squared is 4. Plug in 3, and so on, I get a over 2 times 9, a over 2 times 16, a over 2 times 25, a over 2 times 36. It's the same. So what's going on here? What does this mean? Well, if our theory is sound, what this means, right? So here I have 1, 4, 9, 16. Here I have a over 2 times 1, a over 2 times 4, a over 2 times 9. What this means is that when I rolled my marble down the ramp, that the acceleration of the marble was, so conclusion, I'll put that right here. Not only is that table consistent with this table, it tells me what A must be. These things are so remarkably similar. What must A be in order to make this equal to that? 2. So what we can conclude then is that the acceleration of the marble caused by gravity was 2. And then what were my units? Well, my units were Eric's and Alex's. So it must have been 2 Eric per Alex's squared. Okay. So if I choose my units in this way, not only do I see this consistency between the theory of calculus and this result that we got, but I also get for free what my acceleration was with respect to these rather unusual units. Not that you guys are unusual, just the units. Okay. All right. So that's our first connection between the experiment and the math. So let's see. With the time I have left, what I thought I'd do is I'm going to... This is... maybe you've heard of Galileo's inclined plane. Right, so Galileo was a very smart guy, no doubt. He was around he's doing... Let's see, I have it written down. He was born in 1564 and he died in 1642. So he was doing his stuff in the early 1600s. And one thing he was doing is he wanted to know what acceleration due to gravity was. Right? This experiment where you drop two things of different mass and they hit the ground at the same time, that had already been done. So it was established that acceleration due to gravity must be constant, and he wanted to measure it. Step 1 is, you put the marble 2 feet above your hand, and then you time how long it takes. Okay, but that's way too fast. I mean, maybe if you had fancy laser computers, you could time how long that was. But in reality, it's very, very difficult to measure time intervals that are that small. So another idea is, well, why don't you go to the top of a really tall building and time how long it takes to drop? Well, the problem with that is that then when the faster you go, the more wind resistance plays a role. So if you try to drop a marble or a bowling ball from the top of a building, you're going to get a bad result because of wind resistance. So, this was Galileo's idea, and so I did this on the other side. But so he inclined the plane, and he decided, okay, well, acceleration will still be constant, but it'll be mitigated by the board. And then he timed how long it took to get down there. And the way he did that was really cool. Right? So I used my smartphone and the stopwatch on it. Right? He didn't have that. So, and what he did was he used an hourglass, but instead of with sand, it was with water. And so he had this hourglass full of water, and then he let the marble go, and at the exact same time, he let the water go. And as soon as the marble hit the end of the ramp, he stopped the water, and he measured the volume of water he had, and he had a correlation between the volume of water and how long that was. That's a cool way of measuring time. Okay, so now we have our data, right? So it took 1.66 seconds to travel down to the bottom. And what I want to show us is that we don't even need calculus. Using high school math, stuff that we've known for a while, we can extrapolate what acceleration due to gravity is for a free-falling object by using just this information right here. Okay, so it uses a little bit of geometry and some algebra. It's not too hard. I need this formula stuff. Now, Galileo didn't have calculus yet, so he didn't have this formula. But through more difficult means, he was still able to figure out acceleration due to gravity. But I'm going to take calculus for granted. So this formula right here, it's telling us something. Right. So remember that the distance traveled, I'm going to call d the distance traveled by the marble. Right. And that's exactly what S of t. That's S of t, which is equal to acceleration of the marble divided by 2 times the time taken squared. So I'm just, the only thing I've done differently is instead of S T, I'm calling it D. So if I solve for acceleration, then we get that acceleration is, okay, so you multiply by 2, divide by t squared, you get 2 times d divided by t squared. Okay, so this formula is much more difficult to arrive at if you don't have calculus at your hands. So let's just take a second to appreciate that that was really easy. And yes, thank you, calculus, thank you. Okay, so now this is a handy formula for it's the acceleration of an object moving in a straight line if the acceleration is constant. And that's the only requirement, is that the acceleration needs to be constant. If acceleration is constant, then this is a formula for acceleration. It's 2 times the distance traveled divided by time squared. Okay? So with this, we can very easily find the acceleration of the marble rolling down the ramp. Right? So for example, the acceleration down the ramp then is going to be 2 times, now I'm going to use feet. So the distance traveled was 6 feet. Divided by the time taken, and so it was about 1.66 seconds squared. Okay, now, can anyone do that in their head? I wrote it down because I can't do that in my head. Here it is. So this turns out to be 4.36, and what are my units? Feet per second squared, right? Okay. Now wait a second. So some of us might have some knowledge. Does anyone know what acceleration due to gravity is in feet per second squared? Wait, that's meters per second squared. Yeah, 32. Yeah, 32. It's just about 32 feet per second squared. I think it's 32.2 something. Okay, so what we see is that when we lower the ramp the way we did, it significantly reduces the acceleration. Right? So let's say we didn't know that 32. Given how can we figure out acceleration due to gravity? So in other words, we know the acceleration of a ball that's rolling down a ramp at this inclination. How can we use that to find the acceleration of an object in free fall? And it turns out that it boils down to similar triangles. And a little bit of vector calculus. I'm told that there might be some vector calc students in here. Anyone? No? Okay, so I'm going to draw a couple vectors. And you're just gonna, and if you don't know anything about vectors, don't worry, just take some vector calculus. You'll be okay. But oops, you got to take my word for it. Okay. All right, so how are we doing? Okay, I got to go quick. Okay, so we have this ramp right here, and now acceleration due to gravity, you can represent this as a downward pointing vector. And the length of that vector is exactly the value of acceleration due to gravity, the acceleration of an object in free fall. And the most common variable for that is g. We're going to call that g. And now what happens is when you roll the ball down the ramp, the acceleration gets split up into 2 vectors. There's the acceleration that the ball experiences, which is going to be in the direction of the ramp. And then there's the acceleration that gets absorbed by the ramp, and that's going to be represented by a vector. Oops, I didn't draw that very well. Okay, here we go. Right, that's represented by a vector that's orthogonal to the ramp. And take my word for it. So the value a that we got here, the acceleration of the ball rolling down the ramp, is exactly this distance here. And I don't care what that distance is. Okay, so what I have here are 2 triangles, and I observe something. That's a right angle, and that's a right angle. And that's the same angle. Okay, so channel our inner high school geometry. If 2 triangles have 2 same angles, then the triangles are similar. Right? So that means the third angle is the same. That means that this angle right here is the same as this angle right here, because the sum of the angles is 180 degrees. And if 2 triangles have all the same angles, that means they're similar. So I'm going to redraw these 2 triangles. There's this one, the first one, which is 6 feet here, and this was 10 inches here. And then there's the smaller one where, now, okay, wait. So I take this other triangle and I flip it over so it's right here. So here's my right angle, here's this angle, and here's that angle. Okay, so on that triangle right there, which one is my G? It's the hypotenuse, right? It's the side opposite the right angle. So there's my G. And then my A is going to be the shorter one right here, A. And by high school geometry, these two triangles are similar, which means the ratios of their side lengths are similar. So I have a choice here, but I think I'll do A over G. Since the triangles are similar, A over G is equal to, well, okay, now I gotta be careful. That's 10 inches, this is 6 feet. Okay, so before I write this down, 10 inches is how many feet? 10 divided by 12, 5 over 6. Yeah, so this is 5/6 of a foot. Okay, so A over G must be equal to 5 divided by 6 divided by, what am I, 6. No, yeah, 6. There we go. Oh, so it's 5 over 36. And in general, let me just point out, I was using these variables d and t. So what, in general, let's come up with a general formula. This is d, that's distance traveled. And let's call this height for height, h for height. So in other words, this is just h over d. Okay, so in my last few minutes here, let's solve for g. And at first I'm going to do it in terms of d and h because I want to get a general formula and then I'll plug these numbers in. Right? So if I solve for g, I cross multiply or do whatever you want, and you get that g is equal to a times d divided by h. You solve for g, that's what you get. Solve for g divided by that. But now we have a formula for a, it's this over here. Right? So I'm going to plug that in over here. And we get that g is equal to, well, okay, so a is what? 2d divided by t squared times d divided by h. Okay, g is equal to, let's see here, 2d squared divided by h times t squared. Okay, so that's a nice handy formula for acceleration due to gravity in terms of the height of my ramp and the length and the time taken. Okay, so now this will be the conclusion. Like I said here, time taken was about 1.66. I did this many times. I measured and measured and measured, and I got anything from 1.60 to 1.75. I was in that range. But the average was about 1.66. So I took the average of all my experimental data. And so rather than just plugging in 1.66, I want to show you a table. And what this table is going to do is it's going to give us an idea of how precise you really need to be when you're timing this thing. Okay, so here's t, and then here's g measured in feet per second squared. Okay, right, I'm using this formula. So if I plug in t, oh, and by the way, so like I said, d was 6, h was 5/6. You plug those two numbers in, and you plug in your values of t. So I plug in 1.6 to see how that was, and I tried 1.63, and I tried 1.66, which is what I really thought it was, or something like that, 1.67 maybe, and then 1.69. And I wanted to see how far off I was going to be, depending on how far off my measurement was. So here are the accelerations due to gravity I get. I get 33.75, 32.51, that's too big, that's a little too big still. 1.6 is I got 31.35, that's a little too small, and then sure enough 1.69 was 30.25. Right? So I had to be pretty darn accurate to get the known measurement for acceleration due to gravity. You see, if I'm off by just a few hundredths of a second, I get a pretty big change. Right? So nonetheless, after considerable effort, I got pretty close to what people say it was, right? 31.35. And actually, you would expect it to be a little less because there is friction. Okay. All right, so I'm pretty much out of time. I was going to talk a little more about more advanced topics, but I don't have time for that. So let me just leave you with this, which is the people in the scientific and mathematical communities who make the biggest impact and who get their names remembered are the people who can bridge this gap between math and science, or math and industry. And all of or not all, but many of the answers to all these big questions out there exist in math world, but someone has to figure out how to find it. So to all the students in the room, I hope that you'll think about that gap as you're studying math and other subjects, and try to think about how you can make the connections. And if you make a really big connection, maybe you'll become famous. Okay, so thank you very much.
Are there any questions?
Sam.
So when they say 32 feet per second for gravity, that's really just some kind of average of measurements too, right?
Yeah, right.
It, it varies if you're near the equator. Or
Yes. And how your altitude,
So,
yeah.
so maybe you were, I know.
Yeah, maybe so. I was up at my house, which is about 2,000 feet up.
Yeah.
Yes, it should be a little less. It's possible. Yeah.
Did Galileo get a number or just?
Yeah, that's a good question. So he did get a number. So he like equated the amount of water to seconds, and I couldn't figure out how close he really was. And I'm still looking for that. If you find out, let me know. Yeah, I'd like to know how accurate he got. Any other questions?
We'll have pizza after the talk down in Darwin 108. So please come down and talk to the speaker some more, and let's thank him so much.
Thank you.